Greetings, friends of astrobiology. Welcome to a brand new episode of Ask an Astrobiologist, a show where we celebrate science and celebrate scientists. My name is Sanjoy, and this program is made possible by contributions from the NASA Astrobiology program and the non-profit Blue Marble Space. Last month, he had the great privilege of having at this very seat Dr. Graham Lau talk to Dr. Amanda Stockton at Georgia Tech, and they had a fantastic conversation on life detection technologies, fieldwork in Iceland, and how to detect life on Mars. This week, however, and today especially, we are going to go far away into the solar system, and we're going to explore and talk about the moon Titan, which is the second largest moon in the solar system that orbits the beautiful planet Saturn. And in order to do that, we'll be talking with Dr. Morgan Cable, who is a scientist at the famed Jet Propulsion Laboratory in the city of Pasadena in the United States. But before we talk to her, it's time for your monthly background quiz. Hope you all saw the message on the social medias. Mike, if you can put up the background from last month. Many of you got it right. I think over 40 of you got the correct answer. It is, of course, the Pamukkale terraces in southwest Turkey. Those are travertine terraces, and the water comes out from those hot springs full of calcium carbonate, and as the CO2 degasses, the rocks, the carbonate rocks, precipitate down to form a gel and over time solidify. They've been used as pools for humans for medical reasons for thousands of years. In fact, there's a Greco-Roman ruin at the top of it. But humans, as they do, started to damage it as more and more people got to it. It was declared a World Heritage Site in 1988. So now you can only enjoy it with your eyes. So we have 3 winners. The third place gets the NASA stickers. It is Seren Nural, congratulations. And the second place gets the NASA stickers as well as the Astrobiology comic novels. And those go to Anthony Adler. Congratulations, Anthony. And the first place gets the stickers, the graphic novels, and the pint glass goes to @Organism1974. Congratulations to all of you. Next month, we'll be giving out prizes for those of you who can guess what my current background is. So enjoy. If at any time during the show you have questions for Dr. Cable, please put them on the SIGINT chat, put them on Twitter with #AskAstrobio, or write in your comments on Facebook Live. And here we go. So, Morgan, it is great to have you on the show. Welcome.
Hi, Sanjoy. I'm so happy to be here.
Oh, you have no idea. I'm loving those Saturn earrings here. They look great. Like we like to do, we're going to talk about so much science today. I'm very excited. But what we like to do on this show is get to know you a bit more as well. And we're wondering, like we like to do on this program, is turning back the wheels of time. If you have any stories on what made you interested in science to begin with.
Well, I actually grew up in Florida in a little town called Titusville that is right next to Kennedy Space Center. And so as a kid growing up, I thought it was just normal to have rockets kind of going off in your backyard. Actually, all of my elementary and middle schools, we would time our fire drills around launches. So whenever a space shuttle was going to go up, we would have our regularly scheduled fire drill. We'd evacuate outside, and we'd get to watch the launch. And I thought that was just like a normal thing. So it definitely had an impact on me. My dad actually worked for NASA too. He was a chemist. So I had inspiration all over that, testing the boundaries of exploration, both in terms of taking people there and also extending our senses with robots. I knew that this was something we could do. I knew I loved science and asking interesting questions and then going out and figuring out the answers to those questions. And so when I realized that could be a career and I could do it for stuff in space, that was a no-brainer.
That's so exciting. I went to university in Florida as well, and I used to run out of class during shuttle launches. We didn't have any fire drills or anything, but just run out of class, even, during the professor lecturing, look at the rocket, whoa, and go back to class. I got in trouble a few times, but it's awesome.
Worth it.
So then afterwards, you went to do your PhD at Caltech, but before that, how did you decide that you wanted to be a doctor of science?
Well, my dad had a PhD in chemistry, and so I sort of saw from him what that career path could be like. And I'm actually a triplet. My brother and sister ended up becoming MDs, the other kind of doctor. But we all sort of through school kind of pushed each other to do better and to work harder and to achieve more. And that's a lesson that I carry through actually until today. There's a saying, what is it? If you're the smartest person in the room, you're in the wrong room. Surrounding yourself with people who challenge you. is a lesson that I think is really important, and it's one of the reasons why we're able to do the amazing science and technological achievements at JPL that we do every day. So I had that inspiration when I was an undergraduate student. I stayed in state. I went to a college called Florida Atlantic University for my undergrad, and I did a summer internship out at JPL. Now, I strongly encourage this. Anyone who is an undergrad, I think there are also programs for high school students and graduate students as well. Do an internship. It's a great way for you to figure out whether it's a NASA center or industry or what have you. It's a great way for you to actually go there and figure out if that's a place that you could see yourself working in the future. And you can network, you can expand your network to be able to connect with people that can potentially hire you one day. It's a great opportunity. So I did that and ended up falling in love with JPL and with Caltech. And that's what solidified my choice to go to Caltech for graduate school in chemistry. So I sort of followed in my dad's footsteps that way.
And did you benefit from professors in terms of who cared about you as a person rather than you as your academics? In other words, did you have mentors that helped support you as you went through Caltech? I mean, it's not an easy university. Tell us more about that support network you had.
Yeah, so Caltech was a very challenging environment, but also a very supportive one. They actually encourage a lot of collaboration, and mentoring was a big part of my education and continues to this day. Whether I went out and sought my own mentors, whether they were chemistry professors, people in my field or outside of my field, and even at JPL, there's actually an official mentoring program that you can join to help link you with people who have a sort of higher level view of all the different projects going on and sort of where you might fit best in terms of your skills. I think that whether there's a formal program that exists wherever you might be, or if you're willing to just reach out to people either at your current level, your peers, or who are further along in their careers, mentoring is a really amazing opportunity you should take advantage of.
I echo all of those words.
Yeah.
So chemistry is a very broad discipline. What got you interested in astrobiology in particular?
Well, I've always loved, to me, chemistry is the language through which the universe communicates, right? It's sort of the fundamental building blocks of biology, right? Physics mostly deals with like atomic interactions, right? Atoms, but it's once you combine them into molecules and then you see how those molecules interact and react with each other, that's where all the interesting stuff happens. And so for me, I was always fascinated in that. And actually, this goes all the way back to 8th grade. I was an 8th grade middle school student, and I needed to do a science project. At this point, I had already been interested in NASA and planetary science, and I ended up forming a project around the question, is there life on Mars? And even at that middle school level, I was able to put forth a question that was based on this interaction that basalt, a volcanic rock, has with liquid water. It's called serpentinization. It creates hydrogen. And I had read an article in Science News about this bacteria. Actually, it was a community of all sorts of different microorganisms that were living off of that hydrogen source, and then CO2 was their source of carbon, an inorganic source of carbon. And that was all they needed to survive. And I'm thinking, okay, well, Mars has had volcanoes, so it's got volcanic rock, it's got a CO2 atmosphere, and deep down underground, it may have liquid water. So if it has all those three ingredients, maybe this form of life could live there. And so I did, to the best of my ability as an 8th grade student, tried to replicate that environment. And my dad actually helped me. He was a professor part-time at a local community college. Since you're not allowed to grow bacteria at home, we would go there every 6 hours to check the growth of my bacteria. So I was waking up with my dad like every 6 hours to drive there. And in the middle of the night and stuff. But it was a wonderful experience. And I think that was the first taste that got me really hooked on astrobiology, the hunt for life, the question of, are we alone in the universe? We have the technology now to try to answer that question, at least in our own cosmic backyard. It's a pretty amazing time to be a planetary scientist and studying astrobiology.
Yeah, it's a great time to be alive. I think we will be the generation of humans which will be able to answer whether or not we're alone in the universe, which is, it's awesome. It's just an incredible time to be alive to do science. So the Cassini spacecraft launched in 1997. I remember it quite clearly, actually. I think I have my name in one of the CDs that's on the spacecraft. You were involved with Cassini pretty early on, right, in your career?
I actually wasn't involved early in Cassini's history, but early in my career at JPL, during the last couple of years of the Cassini mission, Linda Spilker, who's the project scientist, Dr. Linda Spilker, invited me to join as something called a Project Science Systems Engineer. Now, I know that sounds complicated, but basically I was the liaison between the scientists in the mission and the engineers that are working on the spacecraft. And that communication is really important because sometimes scientists and engineers may speak in different languages. And ultimately, the more the engineers understand the science that we want to accomplish, the better that they can, say, plan sequences of Cassini, like what instruments are pointing where, and those types of sort of engineering problems. And then the better scientists can understand the engineering constraints of a mission, they can frame their science questions better to best use the instruments to their full limits without trying to exceed that. We always say at JPL that the scientists want to go to the interesting places, the engineers want to go to the safe places, and we need to find, the areas where that Venn diagram coincides. And so it was a really amazing experience. The Cassini mission, like you said, it launched in '97, but it was built before that, right? And there are people who have been working on Cassini their entire careers. Cassini arrived at Saturn in 2004 and did science for 13 years before we did that elegant swan dive during the grand finale where we plunged into the atmosphere of Saturn. And during that time, the Cassini team really became a family. And to be welcomed into that family near the end of the mission was such an amazing experience. I got to learn from people who had been doing this science and this engineering for decades. And being able to carry that over into future missions is something that's really critical, I think, to be able to have us be at our best when we're exploring, especially the outer solar system.
That's fantastic. So in 2004, something else really exciting happened. The Cassini spacecraft had a piggyback of another payload called the Huygens probe, which separated from the spacecraft and went through the atmosphere of the moon Titan and landed on the surface. This was in collaboration with the European Space Agency. I remember refreshing the ESA webpage furiously as the thing was coming down to get the first pictures. And we saw those first pictures. We saw a world that we're almost familiar with. If you were to stand on Titan today, Morgan, bring us there. What do you see? What do you smell? What would it look like?
Awesome. Yeah, I love talking about Titan. Like you said, it's the second largest moon in our solar system. Actually, if you count its atmosphere, it's the biggest. But we'll let Ganymede, have something because Titan, I think, is way more fascinating. Sorry, Ganymede fans. If you were standing on the surface of Titan, well, picture this. The atmosphere is about 1.5 times thicker than Earth's, so you wouldn't need a spacesuit. You'd need a really, really thick parka, though, because the average surface temperature is 90 Kelvin, which is minus 183 degrees C. I don't remember what that is in Fahrenheit, because I'm a scientist, we don't work in Fahrenheit, but it's really cold. So you need some kind of really thick parka to keep you warm, and you need to bring your own oxygen, because there's no oxygen in Titan's atmosphere. But it is nitrogen-rich. It's got a lot of nitrogen and a lot of methane. So if you were standing on the surface, you would feel, I think it would be the equivalent of you about 10 feet down in your swimming pool in terms of the pressure you'd feel. So if you have a swimming pool, just go to the deep end and dive to the bottom. That's about what you would feel for 1.5 bars of pressure. But because Titan's atmosphere is thicker and its gravity is less, it's about 1/7 that of Earth's gravity. If you had wings and you flap them, you could literally fly. You'd float off the surface of Titan and you could fly around. So it's a really cool, like, alien environment when it comes to being able to interact with it in that way.
So would you be able to see Saturn? Would there be enough light because it's so far away?
So what I've heard of in terms of the lighting would be the equivalent of if you were sort of standing in a parking lot at dusk, I think one scientist said. I don't know why they picked a parking lot, but that was the expression. So imagine like things are really dim. But that's in terms of the sunlight coming from Earth. You might get some Saturn shine as well. But Titan also has multiple haze layers. It would sort of be like if you were in LA in dusk on a really smoggy day or smoggy evening. And so it might be difficult to peer and actually see Saturn itself through those haze layers. Essentially what happens is it's sort of like how smog is generated here on Earth. For Titan's atmosphere, you start with the two main ingredients, which is nitrogen, N2, nitrogen gas, and methane, CH4. So you've got N, C, and H. Now, if you have your chemistry set, which I have somewhere here at home, but if anyone else has one, you just put those three atoms together in whatever combination you can think of. Small molecules, big molecules, all of those exist on Titan. They're mostly formed by UV radiation. There are other energy sources too. In the atmosphere, they break apart those molecules and they'll form all sorts of things. Some of those will form those haze layers that we see. It's the same way that smog forms here on Earth. And you'll also form particles that then rain down on the surface of Titan. We actually think that's what the dunes are made of. Titan has a bunch of dunes in its equatorial region, sort of the waistband right around the equator of Titan. And it's also got these liquid methane and ethane lakes at the poles. Titan has weather, just like Earth does. It has clouds, rain, potentially snow too. And we see these river channels and gullies that have been etched because of these erosion processes. Just like we have on Earth, we have them on Titan too, but they're made by a different liquid.
So it's not water, it's like rain of methane that forms lakes. And so it's very familiar almost. It's terrain that we know. I mean, it's not an alien terrain to the point that we recognize the rivers, we can recognize the lakes, we recognize the rocks, but the rocks are different, right, on Titan?
Yeah, it all looks similar, but it's made of very different stuff. And that's one of the things that I and colleagues are trying to understand in the laboratory. It turns out Titan is not that hard to replicate in the lab. We use something called liquid nitrogen, which has a temperature of about 77 Kelvin. Titan's surface is 90, so you just make some cryostat, is what we call it. Cryo is cold, stat is just stay, so it's a way of maintaining temperature. And we'll start it off by cooling it down to liquid nitrogen temperature, and then you just have to heat it up a little bit, and then you've got Titan. And as that liquid nitrogen boils off, it makes a nitrogen atmosphere, very similar to what Titan's is like, and then we can do experiments. We also have some more sophisticated ways of generating those same conditions, but in principle, that's all we're doing. Now, once we do that, then we can take different molecules that we know to exist on Titan because of the Cassini-Huygens mission, both the probe and orbital observations from the Cassini spacecraft itself, and then we combine them, and so far we've been very surprised, even combining simple things like benzene, which is a solid, and ethane, which is a liquid. You mix those two things together and you form essentially a Titan mineral. We think of it as something similar to a hydrated mineral here on Earth because ethane is part of the liquid phase of Titan, just like water is part of the liquid phase here on Earth. What we're finding is these minerals may be ways of storing or moving or being able to change some of the surface properties in ways that we might not expect. And this can be important for answering a lot of big questions about Titan that are still unknown. One of those big questions is, if you look at the atmosphere, you've got nitrogen and methane, and over the history of Titan, if you believe it's been around since like the beginning of the solar system, which is what, 4.5 billion years, then we should not just have lakes on the surface of Titan, but we should have an ocean. All of the methane and ethane that's formed and stuff should have rained down and made a really thick ocean. But it's not there, and we don't know why. One of the reasons, maybe there are some minerals that are sucking up some of those liquids and storing them underground in reservoirs that we can't see. So that's one of the questions we're trying to answer with our laboratory work.
That's fascinating. So it's almost a new discipline, right? Titan petrology, the study of rocks that are not silicates like we're familiar with on Earth.
Yeah, totally. I remember the first time we sat in the lab and we were looking at some of these molecules with our instrument, and we saw some weird peaks come up. And one of my colleagues said, that's weird. And you love that in science, especially as an experimentalist, because that's when you know something cool is about to be discovered, maybe. And in this case, that was the case. So we found this first Titan mineral. Since then, we found a couple others, and we have hints at a few more. And because of that, one of our colleagues, her name's Helen Minor-Casely, she's a scientist down in Australia. She works in the Australian Nuclear Science and Technology Office, and we've been collaborating with her to get crystal structures of some of these. And she recently wrote a paper talking about this new field of Titan petrology. It's a really exciting time. And as a chemist doing organic chemistry, now I need to learn a lot more about mineralogy and geology and all of these things. So we've been picking the brains of some of our colleagues to try to understand how these organic molecules now are behaving like minerals and what that might mean for surface features we see on Titan, or maybe even life.
Let's talk about life in a second. I definitely want to go there. But first, again, for those of you who are watching, don't forget to use hashtag AskAstrobio if you want to ask us a question on Twitter. If you're watching on SegaNet, use this chat function there. If you're on Facebook Live, put your questions down in the comments, and we'll get those to Dr. Cable shortly. But let's talk about life on Titan. So the surface temperature on Titan is colder than the lowest temperature that life has been identified with on Earth. So we need to think more creatively about chemical processes that could be identified possibly as life on Titan.
You do. And actually, I should take a step back and say that there are really two environments where we might find life on Titan. There's the surface, which is sort of weird and alien, and we'll talk about that in a moment. But there's also the subsurface. Just like Europa, Enceladus, and a lot of these other ocean worlds, Titan also has a global liquid water ocean underneath all of the cool stuff happening on the surface. And so that ocean is probably much more amenable to life as we know it. So if we wanted to find bacteria that lived in water, that would be a place to look. Now, it may be really hard to drill down into that ocean. It's the crust is, I forget, it's tens to maybe 100 kilometers thick, something like that. And so getting down there might be tough. There are a few places on the surface where we see evidence of what we think are cryovolcanoes. That's a place where some of that liquid water might have gotten pushed up and formed this cryomagma that spilled out on the surface. And that would be an excellent place to try to look for life as we know it, or at least evidence of it. But, like I said, there's this other environment, this alien environment that exists on the surface. This is where the liquid phase is not water, but ethane and methane, hydrocarbons. Now, from a fundamental chemistry perspective, water is what we call a polar solvent. Methane and ethane are non-polar. Now, if you remember your basic high school chemistry, like dissolves like, right? You can't dissolve oil in water. You can dissolve it in methane and ethane. There are very fundamental differences to these liquids, what they will dissolve, how they might react, which tells us that any life that were to exist in a methane or ethane lake would have to be very different, just chemically, from any Earth life that existed in water. So there's the fact that the solvent is different, the liquid is different. But also, like you said, the temperature is different. Now here on Earth, we're happy at, 75 degrees Fahrenheit there. See, I used Fahrenheit. Or warmer. And like you said, the coldest, I can't recall what the coldest temperature that life has existed in. It's sub-zero, but not too much below that. That's still a balmy, super hot day on Titan, right? And whenever, for a chemist or a biochemist, whenever you cool things down, reactions slow down, or they may stop completely, right? Chemistry becomes very different at these low temperatures. And so one of the things that we are trying to understand in the lab is what tools some sort of weird alien life might use in this very cold environment. I'll give you an example. Earth life, all Earth life that we know of, uses one energy molecule. It's called ATP, adenosine triphosphate. And the way that your cells in your body and all microorganisms and giraffes and tube worms and everyone uses the same energy molecule, the way that you transfer that energy around is by making or breaking a covalent bond. So you add or subtract a phosphate. And that's a covalent bond that you use to do that. Well, that's fine here on Earth. That you've got to dump some energy in to break the bond, but then you get some energy out at the same time. But on Titan, a covalent bond is really, really tough to make or break. It requires a sort of the equivalent of a lot more energy at those low temperatures. Now, on Earth, we have different types of bonds. We have hydrogen bonds, things called van der Waals forces or dipole-dipole interactions. Fancy words for basically bonds that are a lot weaker. Now, here on Earth, they're not quite as useful for, say, trading energy around. But on Titan, maybe those weaker bonds would be much more important. A weaker bond might be the equivalent of a covalent bond here on Earth. And so we sort of have to take a step back and rethink how we might look for life, or the basic tools that life might use to make bonds, break bonds, and form the molecular machinery to be alive. So those are some of the questions that we're trying to address in this alien world that's Titan's surface.
That's fascinating. Absolutely fascinating. And it just shows the danger of having an anthropomorphic view of life in the universe by just knowing the only kind of life that we do know, which is Earth life. So awesome that you think about these new chemical ways that chemical systems could perhaps evolve into something biological. Really cool. Speaking of planetary surfaces, you're also involved in the exploration of another planetary surface on a moon around Saturn, and that is the surface of Enceladus, right? No, Europa Lander around Jupiter. I'm sorry. But tell us a little bit about your involvement in the lander that's going to explore the surface of Jupiter, of Europa, hopefully.
Sure. Yeah. And I would love to talk about Enceladus too. That's an amazing world, like you said. Europa is a fascinating place also. Currently, NASA has one mission that's definitely going to Europa. That's called the Europa Clipper mission. I'm a collaborator on one of those instruments aboard that mission. And that one is going to do orbits around Jupiter and then flybys of Europa. And it's going to map the surface in higher resolution than we've ever done before. The instrument that I'm a part of is called MISE, Mapping Imaging Spectrometer for Europa. And that will help us get at the composition of the surface. We're still not sure if there are some places that are rich in salts, like magnesium sulfate, or if they're rich in things like sulfuric acid, which might not be as useful for life. So there are all sorts of interesting questions that the Europa Clipper mission will address about Europa's history, its habitability, its potential to hold life in its subsurface liquid water ocean. So that mission is really exciting, and that one's moving forward. I'm also part of another mission concept that would actually land. Like you said, this is called the Europa Lander. It's still in what we call pre-phase A, so it's not a real mission yet. It's still a concept study. But we've done a lot of work on it, our colleagues at JPL and elsewhere, to develop the ideas that this mission would try to address. And the goal here, I mean, this would be the first time we would land on an ocean world without an atmosphere, right? The Huygens probe, the collaboration with ESA, landed on Titan. That had a very thick atmosphere. It's a much different landing architecture because you can use parachutes and things like that. On a place like Europa, you can't. So we're working on some creative ways to be able to safely land a payload in this alien environment where the highest resolution image we have right now is only 6 meters per pixel. Now, it turns out we've done some similar things on Mars, where we didn't have very good imagery of the surface, but we're still able to land safely. So we're taking a lot of those tools and that knowledge and experience from the Mars community and applying that to Europa. It's a really exciting time. I mean, could you imagine, what if we land on the surface and we cut into that ice and we collect a sample and we find evidence of life there? How amazing would that be?
That's incredible, yeah. So you're involved in exploring the entire solar system, it seems. What a career.
Well, there are so many amazing places to go. I mean, it's hard to say no when someone says, hey, we're working on a mission concept to go to Titan or to go to Enceladus. You know, what am I going to do? Oh, no, I'm too busy. That's not a very exciting place. Of course I'm not going to say that. But it is hard. You want to not say yes to everything. But yes, in particular, Titan, Enceladus, and Europa, those three are just, they're so fascinating and they're so deserving of more exploration. I really hope we get to do as much science as we can, in our lifetime, and preparing the next generation for making new discoveries there. If anything, Cassini and Galileo, these missions to these outer planets, they've taught us that, every time you go there, you find something new, something fascinating that you want to explore further. And it really helps us hone our science and the questions we want to ask for next time. But we always come up with new questions, too.
Your enthusiasm is just oozing out of the screen in front of me. It's fantastic. Many of our perhaps younger viewers are wondering, how does one become a scientist at JPL? Do you have some words of advice for them?
Oh, sure. That's a great question. I think in addition to studying a science, one of the most important things is to stay curious and stay motivated. Because planetary science is such an interdisciplinary sort of field, you can study anything from biology to chemistry to geology, astrophysics. All of these things you can apply to planetary science and become a scientist at a NASA center like JPL one day. So don't pick a major because you think that's what they want. Pick something that you enjoy, that you're passionate about, something that you would do for free, that you didn't even need to be paid for. That passion is going to follow you throughout your entire career. And if it's something that you can tie in to planetary science or astrobiology, all the better. But we have not just scientists, we have engineers that work on these missions, of course. We have journalists, people who help us with our media campaigns and help us communicate to the world. We have artists. JPL has a few resident artists that help us with our outreach. They'll help us with mission proposals and all of the beautiful artwork you see on our websites. That's thanks to them. So there are a lot of different career paths that will take you to NASA. Now, there's something else I mentioned earlier on. Remember how I said I did an internship? That I think is really important too. NASA has a bunch of internship programs, and they're a great way for you to get a taste for what this work is actually like, figure out if it's really for you or not, and then expand that network. It's a lot harder to ignore an application from someone when you know who they are. They've already demonstrated their capabilities because you've seen them do some work and you've built that reputation already. So I really encourage applying for internships.
Fantastic. And we're almost time to open up the conversation to our guests to ask questions. But I do want to ask you about your hobby, which is mountain biking on a unicycle. How did you get into that?
We call it mountain unicycling, or Muni for short. And we basically just got rid of all the stuff you don't need. You know, the handlebars, the brakes, the training wheel, like all of that. Just, you don't really need it. But seriously, though, when I was doing my internship at JPL, so I was still an undergraduate student, I met this really cute guy who was riding a unicycle around Caltech. And so I went up and talked to him and asked him about it, because it was a really unusual looking unicycle. It had a big gnarly tire, like nubs on it. It was really like beefy looking. And it turns out that he had done mountain unicycling. And a few years later, I kind of married him, and now we go riding pretty often. But I love that sport because it forces me to be completely focused. Like, I can't let my thoughts drift off to the work I need to do or the proposal I need to write or the papers I'm working on. You have to be completely focused on what you're doing, because if you let your thoughts drift, you're going to hit a rock and face plant, and that's not so good. So I like it for that. I like it because it's really challenging, and yeah, it's sort of like meditation in motion for me. One of the things I've noticed about all of my colleagues at JPL and other NASA centers as well, you, Sanjoy, are a good example too. We tend to have hobbies where, you know, we'll be passionate and push ourselves as well in hobbies, just like we do in work. And I really love that, because we're all such dynamic people, and it's great to see the different outlets that we push our energy into. You do, what is it? It's navigating, no.
Orienteering.
Orienteering, yeah, where you like get a map and then you go, that's a really useful skill for all sorts of different reasons. And then you race, you like run around, that's awesome.
Yeah, it's something I like to do. You don't know the course prior to the race. The race starts, you're given a map and a compass, and it's like, go. Like, where am I? I mean, go. It's awesome. But this is not about me, this is about you. So let's not talk about me, let's talk about you. But it's time for questions, which is my favorite part of the show. So please ask your questions using hashtag AskAstrobio on Twitter, or put them in the SegaNet chat if you're watching on seganet.org, or put them in the comments if you're on Facebook Live. And the first question is from Marianne Denton. Hello, Marianne. And she asks, what is your favorite Earth analog? In other words, if you could take a car and drive away, where would you go?
Ooh, okay, my favorite Earth analog. Well, I've got one that I could drive to, and one that I definitely would need to take a plane and then do some hiking. So my favorite Earth analog that I can drive to is probably Death Valley. There's a place there called Devil's Golf Course, which, if you haven't seen what this looks like, definitely Google it. It's really gnarly looking. It's this salt pan that has gone through many cycles of getting wet and then the liquid evaporating away. And since it's in Death Valley, it's so salt rich that you end up with these, like, they look like rocks, but they're made out of salt, and they're very sharp. And you know, if you tried to hike on them, you'd tear up your boots and probably get some scrapes and scratches. The cool thing about this place is that from a very low resolution, if you were just to fly over it with a low resolution camera, it would look smooth as silk, like the safest place you could possibly land. But then when you actually get down there or get some high resolution imagery, it's got some crags and some drops and dips and scary stuff that you might not necessarily be okay with sticking a lander on. And so it's a good use case for us to try to test some of our landing capability for things like the Europa Lander concept. That's the one I would drive to. The one I would fly to is probably the summit of Mount Kilimanjaro. When I was a graduate student, I was fortunate enough to be added onto a team where we got to hike up to the top of that mountain and camp at the summit for 4 nights. And it was one of the most amazing experiences I've ever had. I mean, you feel like you're that much closer to space. I can't remember what exactly the pressure is at 20,000 feet. That's the altitude at the top. But it's amazing. And our sample site was like this very short walk away from camp. It was near one of the glaciers, the ice fields, like the edge of this glacier. And it was up this really gentle incline. But since it's at 20,000 feet, you don't have as much oxygen. And I remember like just going up that tiny hill, you're totally winded by the end. You're like, man, I'm out of shape. And then you remember, oh no, we're at like ridiculously high. It's nuts, but beautiful place.
Yeah, I think the air pressure at the top is like half of what we have at sea level.
I think it's something like that. It's pretty intense, very windy.
So one of the key elements for life is phosphorus, at least for life on Earth. And Tom Caruso via Facebook asks, can you explain the possible phosphorus cycle on Titan and possible sources of phosphorus outside of the moon, such as meteors or dust-ring particulates over time that could influence the development of life on Titan or any of the moons nearby?
That's a really good question. Yeah, so life as we know it includes phosphorus as one of its key elements. Like we talked about, ATP, adenosine triphosphate. Phosphorus is a key part of that energy transferring molecule that all life uses. Now, as you get further out into the solar system, further away from the sun, you end up getting enriched less in metals, like Mercury is sort of the most metal containing planet. As you march further out, you get less of that and more of volatiles condensing. So things like ammonia, nitrogen, methane, water, CO2, stuff like that. Now, Titan still has a rocky core. So if there were to be life, in that surface ocean, it's possible that there could be some phosphate that you could get from that environment. There are some models that may have an ice layer between that rocky mantle and the ocean. But I think a few studies have come out that show that even if there is ice there, you can still get exchange over time. And so that could be something that could exist. There's also, like your person who asked the question mentioned, there could be meteoritic infall that could deposit certain minerals and things like phosphates as well. So there are a few sources. They're not going to be quite as abundant, but that just may give us some ideas in terms of life as we know it and what the metabolic limits might be. They might be a more energy-constrained environment because of resources like that. Or life might find a way, like some people might have said in Jurassic Park, and we may end up utilizing different energy transfer molecules and things like that. There was that controversial paper a few years ago about the lake, Mono Lake, and the arsenic that could potentially take the place for phosphate. Now, at Earth temperatures and pressures, that's not very likely. The reason arsenic is a poison is because it is not very stable in liquid water at our temperatures. It tends to undergo hydrolysis. And so what it'll do is it'll replace the phosphate backbone with some arsenic and then just kind of chew it up. That's why arsenic is so dangerous for us. But think about really low temperatures. Well, then the hydrolysis would be slowed down a lot. And let's say you're not even exposed to water. What if you're in methane or ethane as your solvent? Well, then those types of minerals and other things that are different but could behave like phosphate might become more important. I think right now we're at the cusp of just trying to understand the basic interactions between very simple combinations of organic molecules on Titan. Ultimately, we'd like to get to a point where we're testing more complex systems, and we can really start to address these questions of what would be the analog for phosphate on Titan. We're not there yet, but it's an exciting time, and I encourage any of your younger viewers to think about that as a potential area of research for a future career.
Very exciting. The next question comes from Richard Gordon, who asks it via SaganNet. Hi, Richard. And his question is really cool because he cites the work of a mineralogist, Robert Hazen, who works at Carnegie in Washington, D.C. And Bob Hazen has made the argument that the diversity of minerals on Earth's surface corresponds to the increase in diversity of life that has taken over the planet. In other words, a lot of minerals means life has taken over the place. Can we use do we know enough about the mineralogy on the surface of Mars to kind of use that as a proxy for whether or not life is on the surface?
That's a really interesting question. I don't know, but I think that line of thinking of finding a place that is not bland and purely composed of one, whether it's a mineral like on Mars or Earth or an organic mineral on Titan, I agree. We want to go to the interesting places where there seem to be chemical gradients, physical gradients, things like that, because that's what life tends to use. The other lesson that I think we can take so far in our sort of astrobiological investigations at this stage is that no one test is going to tell us whether or not life exists, unless, let's say, some squid emerges from a crack in Europa's surface and waves his noodly appendage at us. Okay, then we might say we just need one test. But typically, especially for microorganisms, we're probably going to need multiple independent lines of evidence that lead us towards ultimately the final conclusion that there is life. Carl Sagan once said that life has to be the hypothesis of last resort. So you must have eliminated all other possible explanations, and you're only left with life. Then that's the most convincing way you can approach that question. And so this mineralogical diversity idea could be very well one of those lines of evidence, but I don't think it would be convincing enough if it was the only one.
Cool, very cool. Thank you for that. And Julia on SaganNet asks about whether you could tell us a bit more what cryovolcanoes are. Like it's not intuitive. We don't really have them on Earth, or do we?
Sure. No, I don't think we have any. I mean, you can make one in the lab pretty easily. But just like Earth has a mantle where we've got lava, magma, right? It's magma when it's underground, and then when it comes out, it becomes lava, right? That's the difference. And so just like magma and lava here on Earth, you can have cryomagma and cryolava somewhere else. Instead of being made of molten rock, in a place like Titan, it would be made of liquid water or a slurry of like water ice, but it's just barely liquidy and kind of viscous because it might have things like ammonia or other sort of antifreeze type molecules that would help to depress or lower the freezing point. So this is something that could exist below the freezing point of water because it's got a lot of salts and ammonia and other stuff in it. It may be sort of really viscous and not super liquidy, but that type of cryomagma, if it were to exist in this environment, there could be different geological mechanisms that could force that cryomagma up through some sort of fissure in the surface where it could spill out on the top of Titan's surface. There are a couple of papers. Rosalie Lopez, I know she's a colleague at JPL, has written about a couple of places on Titan's surface. There's an area called Hote Regio, I think that's one, and Sotra Facula is the name of another one. Places where it looks like this process might be happening, and so we might have a cryovolcanic flow. And these are exciting because, A, it might tell us, if we were to go and sample one of those places, we might have an easy way of accessing some material from that ocean that would be really hard to drill and sample ourselves. And B, this could be a place where now you have liquid or near liquid water interacting with all of those fascinating organic molecules that have been raining down from the atmosphere. Now this is important because here on Earth, when we make those complex organic molecules, we call them tholins. Carl Sagan named it. It's named after the Greek tholos, which means muddy or not clear. I love that because they're like brownish. We also don't really know what they're made of because it's like a soup of all sorts of organic molecules. If you take those tholins and you dissolve them in water, you make amino acids like that. Like, it's crazy. And so any place on Titan where we might find liquid water interacting with these organics, we might find the ingredients for life as we know it. So cryovolcanic flows are a good place. If there's like an impact from a comet or a meteor that created a melt pool that could be stable for a while, that's another good place. Things like this are really fascinating targets for a future in situ mission to Titan.
Indeed, and this leads to the next question by my co-host Graham Lau, who is curious about if you had like an infinite of resources to build your own mission to explore the icy worlds of our solar system, what would you do? What would you build?
Oh boy. Well, I think that's a great question. And I think it would be a different answer for a place like Titan than it would be for a place like Europa or Enceladus. And let me explain why. Due to Titan's atmosphere, you can actually take advantage of a couple of different ways to transport or move your robotic spacecraft around. I'm actually a co-investigator on one mission concept called Dragonfly that would do just that. The PI is Zibby Turtle out of APL, and what this is essentially a rotorcraft that could fly, land, basically do these hops across the surface of Titan. It turns out, just like we were talking about earlier, where if you were standing on the surface and you could flap your wings, you could fly on Titan. It turns out that transporting through air is much more efficient than it would be to use like a typical Mars rover kind of design for an environment like Titan. So I think in terms of exploring Titan, that's the exact kind of architecture I would use. Because then you can move to different places. So we could say we found a cryovolcanic flow. We could land there, collect some samples, do some science, and then we could hop over to the dunes and figure out what the heck those are made of, because we still don't know. And maybe we could hop all the way over to a lake edge and collect a sample there too. There are all sorts of things you could do with that kind of platform. So I think that's what I do for Titan. Now for Enceladus and Europa, oh boy, it depends on how much money I had, I think. If I could like fly through the plume of Enceladus with a lot more detailed instruments or instruments with better resolution and sensitivity than Cassini, I'd definitely do that. But ultimately landing, maybe digging down, drilling into the crust and getting to the ocean and letting loose a submersible, that would ideally be what I'd like to do. Swim around, look for some tube worms by those hydrothermal vents, and officially collect my Nobel Prize. That's what I do. Well, me and my team. Wouldn't just be me.
A few episodes ago on Ask an Astrobiologist, we had Steve Vance. We were interviewing Steve Vance, and he was a science advisor for the movie The Europa Report. So those of you who are watching today, if you haven't seen that movie, go ahead and watch it. It gives you a bit of an idea of what it takes to explore Europa. So we're getting close on time here, but I want to give Preeta the chance to ask her questions, which is very good. And she asks, apart from Mars and the moons of Jupiter and Saturn, what are the other places in the solar system that are most probably habitable?
Oh, okay. Other than Mars and the moons of Jupiter and Saturn. Okay. Well, Triton, which is a moon around Neptune, is really fascinating and really weird, right? It's orbiting backwards, which means we think it might be like a captured Kuiper Belt object or something like that. It's got active cryovolcanoes. It's the one place that's confirmed for sure to have that. Thanks to the Voyager missions, we know about that. So it looks like that could be a really fascinating place. It's not clear if it also has a liquid water ocean. That would be one of the main things to look at the next time we send something there, which, boy, I hope is soon, because that's a fascinating place too. There's been a lot of work with Ceres and some of the larger dwarf planets and things like that in the asteroid belt that are really fascinating. There are these Trojan asteroids that are further out that also could host environments where maybe liquid water could be stable for a certain period of time. Now, we still don't even know how long you need to have the right ingredients for life to emerge, to just sit and wait and have life form. We still don't know what that is. Is it 20 seconds? Is it 20 million years? We don't know. And so I think going and looking at all of these places is really important. Because like you said, Sanjoy, we only have a sample size of one, right? We know Earth is the place we have life here. That's it. That's all we know of. And so by studying all these other places where liquid water may have existed for different timescales, where the temperatures or the pH or the initial ingredients may be different, all of those things we can now bring into our sample size and assess, okay, well, in this environment, there's no life, but it has these conditions. Versus Earth, which has life, has these conditions. And this can help inform our exploration and our study of exoplanets and trying to find life elsewhere as well.
That's so fascinating. And before we close, though, Morgan, I want to give you and the entire Cassini team a huge shout out for the incredible mission that it's been. And I think we're still getting data and analyzing, trying to figure out what it means. But Cassini received an Emmy Award, right? Tell us about that. That's awesome.
Yeah. Cassini's Emmy was for, I want to read it, it was Outstanding Original Interactive Program. And so this was right near the grand finale. We we had a unique opportunity, right? The spacecraft was working perfectly, and we could actually plan the end of the mission. Now, you don't always get to do this. Sometimes things go wrong, like with the Spirit Mars rover, where that was sort of out of our control of when that mission might end. But with Cassini, we knew we were running out of gas, and we didn't want to have Cassini run out of fuel completely and then drift aimlessly in the Saturn system where we couldn't control it anymore. Because Cassini was kind of a victim of its own success. It discovered liquid water on Enceladus and underground on Titan too. What if, by chance, 1,000 years from now, 10,000 years from now, Cassini were to accidentally crash in one of these places and deposit one of its microbial hitchhikers there? We did the best job we could to clean Cassini, but we didn't sterilize it because we didn't think liquid water could exist that far out when we built it and launched it in '97. So because of that, we had to dispose of Cassini somewhere where we knew it could not contaminate that place with Earth life. What would be worse than finally finding life on Enceladus and realizing we accidentally put it there? So because of that, we planned this swan dive into Saturn's atmosphere. We collected data the entire way until we lost signal. And as part of that effort, our media department did a huge outreach campaign. You can still go to saturn.jpl.nasa.gov and find a lot of those same outreach activities, things that we were monitoring. We had some incredible videos and then some live footage of the Cassini grand finale plunge, which was at 5 o'clock in the morning here Pacific time. And it was an incredible Herculean effort. Those media specialists that are on our team were absolutely amazing and very deserving of the Emmy. I mean, they were the ones who did the lion's share of the work, but everyone on Cassini feels like the Emmy is in part a little bit, it's shared amongst the whole team because this mission was just such an amazing success and it touched so many lives. And like you said, the data, we're still going to be analyzing that for decades to come. So it's an incredible thing to be a part of, and I just can't be more proud of my colleagues and friends on the Cassini mission, in particular the media teams that made that possible.
Wonderful. And that's a beautiful place to close. We're running out of time, which is so too bad. I really value this conversation, Morgan. I know you're extremely busy, and it's clear that you are. You do a lot of science. You even travel all over the world to do outreach, to talk about how exciting science is. You're a really excellent role model for many of our young viewers. I just want to thank you for the time you took to speak with us today.
Thank you, Sanjoy. I feel really lucky to be able to have fun. I love going to work every day, and I hope that we can potentially, you and I and all of us who advocate for outreach and science, we can inspire the next generation, because I don't want the science to end with us. We've got to have that next generation come up and continue to do amazing things. So thanks for everything.
Awesome. So you are at Stars Are Calling on Twitter. So if you're on Twitter and you're not following Morgan, please do so. Folks, this is it for this week. We'll see you next month on Ask an Astrobiologist with Graham presenting. And until then, it's good to see you all and stay curious. Bye-bye.